So, guten Morgen. Hallo zusammen. Good morning. Nice to see you again. Today we are quite punctual. Vielen Dank für die Hausaufgaben, für die Ergebnisse. Ich habe diesmal relativ viele bekommen. Ihre Lösungen zum Test 13, teilweise über E-Mail und teilweise über IDS-System. Finde ich sehr gut. Nicht alle Lösungen waren korrekt, nicht ganz korrekt, aber es ist nicht schlimm, es ist kein Problem. Ich werde Ihnen natürlich jetzt ein bisschen erklären, was man vielleicht noch besser machen könnte. So, even though not all solutions are perfect, still thanks a lot because this is an important feedback for me. And I guess you also learn better if you solve problems by yourself. But I'm really glad that this time we have more solutions than usual, and I'd like to encourage you to proceed to also today I'm going to give a little bit harder homework, a little bit more tricky, and I hope you will be able to solve it still. At least you should try. So on the screen, you can see our today's plan. We are going to continue the topic momentum and momentum conservation. So first, we will speak about the solutions for test number 15. Then I'm going to introduce quite a central and important topic to you, which is ballistic pendulum, auf Deutsch. Es heißt ballistisches Pendel, also ähnlich wie die englische Version. Und wichtig ist dabei zu lernen, was die beste Lösungsstrategie ist. So it will be important to notice the solution strategy here. So in order to not to make a mistake. The problem ballistic pendulum is a usual problem in the examinations, so that's why it is worthy to learn it really good. After that, we will talk about diversity of elastic collision problems. I'm going to show two complicated equations which are a bit hard to learn, but you can always derive them actually. And once you have these two equations, they will describe lots of interesting scenarios concerning absolutely elastic collisions. So we will talk today about elastischer Stoß. Ja, heißt es auf Deutsch, über den elastischen Stoß, elastic collisions. And finally, to conclude, I'd like to tell you about the central equation of the rocket motion theory, one of the central equations of aerospace motion. And even if you will maybe not deal with aerospace technique in the future, still that will be a good example of how powerful the momentum of motion is, that this is the central paradigm that, well, this is the basis of rocket motion theory. Okay, das ist der heutige Plan und jetzt der Reihe nach werden wir die Aufgaben aus der heutigen Hausaufgabe kurz mal besprechen. So By the way, I hope that you are fine. I have right at the moment a bit of hard time because of many blog courses still running. Yesterday, whole day lecturing, I have problems with my throat because I was talking all the day long. I was so tired. And today is a little bit, so this classes I'm giving to you is a sort of relaxation to me because tomorrow it will begin whole day lecturing and practicals. And also tomorrow we have a large exam of our bachelor students who are writing the exam in medical imaging technique. That will be a big examination. Okay. Zurück zur Aufgabe 1. So here you have seen 3 different setups, and the task was to guess, to decide which setup, which ship will go in which direction. I should say that wasn't very easy, and for the third problem, there is no ideal solution actually. Okay, but still I hope that everybody were able, at least this is what I saw, that if you're talking about the setup A, just a moment. So setup A, obviously, we have momentum of air particles is given to the environment, so they are lost. And in order to apply the conservation of momentum, and the momentum is conserved in this case, the rest of the equipment should go to the right? So I think most of us could easily recognize that in this case, this ship will move to the right. Easy. One thing that I need to mention now is, and I want to ask you now about this. Let's take first this setup. I will take a box filled with gas. Having some pressure. V. And I will surround this box with vacuum, so nothing, no particles, X. And now I'm going to make a hole in this box, ein kleines Loch, and I think for us it will be quite clear that once I will make this hole, the whole box will start moving, driven by reactive propulsion force. So since it loses particles in this direction, so they will escape the box, right? So, and this will give propulsion force to the box upwards. Well, that's easy. But now let me ask you some more difficult things. So please think about this. I'm going to make same thing, but exactly the opposite. I'm going to take the box, same box. I'm going to take whole air, whole gas out of it. So inside of this box, there will be nothing. And I will surround this box with gas having pressure P. And now I want to ask you, so please think about this. If I make a hole in this case, what is going to happen? The options are A, it will go upwards. B, if it will go downwards. C, nothing will happen. So please think and please let me know what you think. I mean, if you do any mistake, it's not a problem, right? So just I want you to share with me what your intuition tells you. If you have a vacuum box and it is in a gas and we make a hole in it, in which direction will this box move? Upwards, downwards, or it will not move at all? So the question is about this box itself, okay? So will this box, let's assume that it's quite light box, so like a balloon, you know. So with the first example on the left side, it is easy for us to think about this because I guess every one of you has played with maybe air balloon, right? Where you can, when you blow it, so it will, and you let it go, so the air escapes from the balloon and it flies away from you. But this on the right, it is an opposite setup, sort of hypothetical case. So we have one suggestion that may be upwards, upwards, upwards. Okay, everybody agree with A, upwards? So that stays down. Ah, sorry. Yeah, now I see. Yeah, you say down. Mm-hmm. Mm-hmm. Yes. Good. Thanks a lot. I think what you sent to me, it sounds logical. It sounds good. And basically, this is what I would expect from you indeed. But sometimes our physical intuition makes troubles for us. So sometimes our physical intuition, our common sense feeling, they fail to describe what happens. And to illustrate that, let me now play a physicist and say, okay, let me approach it really physically. And for that, I'd like to make our standard physical procedure. I would like to see what kind of forces I see in my first setup and second setup, okay? For that, I will choose now, I will make black color arrows showing in which directions forces applied in first setup on the left and to the right. And after I make this drawing, I may ask you again what you think. So look, assuming we have a container, this box, and the pressure is, there is some pressure in it, and of course, logically, we expect that the particles of gas, they exert same pressure to the left, to the right, up and down. So let me put it as arrows. So I have 3 arrows showing to the up, 3 arrows down, left, 3 right, and also 3 to the bottom. And now what happens, look, as we made a hole, so this arrow, which I will now label green, this force that previously kept the box at rest, so this green force is now sort of has no support anymore, so it goes away. That means that this blue component to the up, it has no opponent force, it has no counterpartner, no opponent, no force it fights against. And that's why now this blue, not balanced component will push the whole box upwards. And this is what we observe. Okay? So, but now let's consider this right case. And let me use the same philosophy, same strategy. I will show the gas pressure as combination of forces applied to the walls of my box from all sides. And at the beginning, I have no hole in it, and logically, all forces are balanced. So the pressure from the right, from the left, from down, from up, all same. My box is at rest. And now I make a hole, I open it. So what happens actually? Look, now, at first glance, it seems that this arrow is not balanced, so it goes into. But look what happens. As it enters the box, it still faces the wall, but not the first wall, but upper wall. So it hits the wall. It does hit the wall, actually, but it hits another wall. But now, please check, if we count the forces acting upwards, downwards, to the left, and to the right, we will still find same number of forces, same number of arrows, 3, 3, 3, 3. So, and indeed, if we make such an experiment in reality, we will see that there will be very slight jerk of the box in the first moment, just a couple of milliseconds, and after that, the box remain silent, remain still, at rest. So actually, the correct answer in this case will be nowhere. It will go nowhere because also in this case the forces will get balanced but slightly different than before. And even if it sounds a bit strange for you, there are such experiments and they show that indeed it remains at rest. It doesn't fly away. Okay, but you see, sometimes it's a bit not intuitive what we expect. And it's always good to make some forces, to make some sketch. Maybe it helps us to see it more clearly, you know, to see it more in more details. And this is what engineers are doing mostly, you know, what distinguishes an engineer from many other people, a scientist or an engineer, is that we try to think more thoroughly. We not always trust our intuition, but we want to check it a little bit more thoroughly. Okay, coming back to the homework, the B case it was a bit difference in your opinion. Some people said it will move to the left, some said to the right, and some people said it will not move. Well, I think this example I showed to you with this box should help us to answer this question, at least theoretically. There will be, on the one hand, some reactive force that will be applied to this part, and it will push it to the right. But on the other hand, the particles which are blown by this machine, they do not escape your system. They remain inside the system, and so they give their force to the sail. And so, in fact, we are dealing with some closed system where no external forces are acting on. And that means you will produce some force here, but this force remains in your system and it applies to your system same way. So here will be force pulling it to the, or pushing it to the left. In other words, this is a little bit the case like if you try to lift yourself by using your hair. And you know it's quite difficult, at least I never managed to do it. So if you're just sitting and try to lift yourself, your body upwards by using your hair and your own arm, you know, it usually doesn't work. Or maybe never works, shouldn't work. So the same thing we have here actually. So the right answer here, it shouldn't work. It will remain, also auf Deutsch bleibt stehen. So A will go to right, B will remain at rest. Yeah, it a little bit depends on size, but we are talking about some theoretical example, right? And you are especially right that it depends for the C case. So here I should say, I admit there is no one correct answer. So here it really depends. So here I honestly also I couldn't say what happens because depending how efficient you are in this case, if you can catch really all particles, then this is one scenario. And if some particles here will escape from your system, then will be something else. For example, if here some particles, let me increase it. So if here some particles will pass by, then the whole setup will move to the right actually. If you catch most of them in a straightforward way, then rather it will remain its position. But only if you absolutely perfectly manage to put all the particles directly so that they do some work on the wheel. So if you, in a very ideal case, if you make them all apply the energy for rotation of the wheel, then in this case it will move to the left. So depending on geometry and the size, as you mentioned, of this C setup, it will move to the right, to the left, or it will remain at rest. So this question has no answer, and that's why good that we don't have this question in our exams, because otherwise it will be confusing. Okay. Aufgabe Nummer 2. Here, zwei Punkte. Here, 2 dots, which you can see here. These 2 dots. Oh, sorry. Small. 9. It doesn't want. Yeah. No. So these 2 dots. It signalizes that from the difficulty level, we are very close to the difficulty level of our midterm exams and final exams. So this is approximately the difficulty level that we should expect in the exam questions. 1 dot means that it's very easy and it is below the examination level. 3 dots means that this is a sort of advanced problem and it may better prepare you for your exam because it's a little bit harder than the exam problems. Okay, das heißt, bei der Aufgabe 2 haben wir ein ganz normales Problem, die Schwierigkeitsstufe Mittel. Und ich freue mich, dass die meisten das geschafft haben. Aber auch da haben manche von Ihnen nicht aufgepasst. So, unfortunately, even at this problem, some of you who I think are strong enough to solve it, you made some mistakes. So, I think because you were not attentive enough. So, let me explain what it was. Obviously, we have to check these two equations, so we can say m multiplied by v is 100 kilogram meter per second, and mv squared divided by 2 is 500 joule. And so these are the things, and our goal is to find out the actually mass, the speed, and the height. Everything is possible. Most of you did as well, but you should be just careful in combining these two equations. Here you have at least two options. So the one is, you can see that here we have this mv component, and here we also have mv multiplied by v. So you can convert this formula as momentum multiplied by speed divided by 2, and it will be 500. And here some of you did mistake that instead of writing v, you wrote v cubed, v in the power of 3. So just mathematical mistake. It can happen, of course, but please be careful. Do not make this mathematical mistake. So this power 3, it is wrong, right? So it should be just pv divided by 2. Or you could do it another way, and from this first equation, you just define mass as 100 divided by v, right? This is your mass is 100 divided by v, and now you put this mass into this equation, and then you can solve this equation for some unknown variable. So in other words, you can say that 100 times v divided by 2 is equal 500 joule. So obviously from here you can find easily that your v, your speed, should be 10 meters per second. The mass is also very easy to find, and will be obviously 10 kilogram. And to find the height, I think most of you did it really well. You just used the conservation of energy principle, right? So you said that we can say that mgh is equal mv squared divided by 2, and that was 500 joule. And since we already know that speed is equal to 10 and mass is also equal to 10 kilogram, that from here we can find the h. So h will be equal 500 divided by 10 multiplied by 10, and it will be equal 5 meters. So basically, we can easily solve it, no problem. We use simply the equations we learned. Height is equal 5 meters, and the mass is equal to 10 kilo. So shouldn't be a big problem for you. Just be careful, be concentrated, right? Do not lose points here. Und jetzt haben wir die letzte Aufgabe erreicht, die Aufgabe 3, und die hatte nur einen einzigen Punkt hier. Das heißt, die Aufgabe war wirklich ganz einfach, wesentlich einfacher als die Aufgaben in der finalen Prüfung. Und trotzdem war diese Aufgabe nicht ganz einfach, weil manchmal eine bessere Antwort möglich war. So, again, thank you so much for having written your ideas and explanations also for this problem. But let me suggest what I expect to be the perfect explanation in each point, okay? So first is the energy conserved in this process? Obviously, they mean mechanical energy, right? So it should be mechanical energy. And in fact, you have two processes here. Two things happening. First thing is that the bullet strikes the block, and second process is that the block is moving along the plane. So you have to specify actually which process is meant. But luckily, in both cases, you should say no, mechanical energy is not conserved, but the reasons will be different. The reason why the mechanical energy is not conserved as the bullet hits the block is because this collision is inelastic. And please also remember it very good that every time you have an inelastic collision, that means two bodies remain stuck to each other, remain one body in the end. In all these cases, energy conservation never applies. Energy is never conserved. Oops, sorry. So this is what I want you to mention always. Please always check, is it an absolutely elastic collision or not? If it is not absolutely elastic, always say energy is not conserved. Second, it is also not conserved because of friction force is involved in this process, and this is the second option, which you can also mention. So there is a non-conservative force that performs work, and this force is friction, and every time it happens, mechanical energy never conserves. But please never forget this first explanation. If collision is not elastic or not absolutely elastic, energy is never conserved. And this is what we see here. Next, point B. It is a bit tricky again, but we are learning how to address those things. The answer is yes. Sounds maybe strange for you, but in that case, we can always say yes for two reasons. One, because the rule says momentum is conserved for any collision, doesn't matter elastic or inelastic. For any collision type. Elastic, inelastic, partially elastic, perfectly elastic, doesn't matter. Momentum conserved always for any collision situation. And that's enough actually as an explanation. But if you still have some doubts and you say, but what about the second part? As the block moves and, well, it stops, so obviously its speed remains less. So what about this? So obviously this momentum of the block, of this box, at the beginning it was high after collision with the bullet, and then it is getting slowly and slowly, and mass remains same, but the speed decreases. So I say, look, the momentum decreases. Well, the answer for that is the momentum is still conserved, but we should not consider this box as an isolated object. It interacts with the Earth by using friction forces. So the total momentum of this body and the Earth remains still constant. In other words, in our task, what we observe, the speed of the box is decreasing because the box gives its energy to the Earth. So the speed of the Earth is slightly increasing. So also in this case, a physicist would say that momentum is conserved, because we should see not one box only, but the box in combination with the whole Earth. That's a bit tricky, I know, but this is how physics works. Yeah, I know that it is sometimes a bit confusing, yeah, but this is what we are doing, right? So we're checking different things and we discover what is true and what is maybe not. Actually, I'd like to ask you one more question, which I think is quite funny, maybe. Let's consider well, let it be like a barrel, like a container on the wheels. And the container moves with some speed v, which remains constant because there is no, let's assume, no friction. And now it started raining, so the rain started. And the rain's direction is sort of always perpendicular to this motion of this car. So what would you say? What happens with the speed of this barrel, of this container? Will it remain same with time, or will it change with time? So what do you say? As it continues driving and the rain is filling it slowly with water. Okay, thank you, Omar. Somebody else? Okay, very good. Thank you everybody who answered. We have different options here, so it may slow down. It can remain same. Nobody said that it will get faster, but we have at least two options, that it remains same or it's getting slowly. This argumentation that it is related to friction, please don't apply it because it's a little bit more, it's not obvious or it's not clear. You cannot prove it actually. Let me give you a better explanation, more clear way to show that the speed of the system must decrease. It will decrease. The explanation is following. From the one hand, the rain droplets having some little masses and momentum, they cannot change the speed of this wagon, of this barrel directly. They cannot change it directly because they are directed perpendicular to the momentum. So we have one momentum of the rain in this direction and another momentum of the car in this direction. So at first glance, you say these two momenta are perpendicular to each other, so they cannot affect each other too much. But at second glance, you will notice that as we observe this barrel with time, its mass will increase, right? So if we say that the momentum of this barrel should remain constant because there is no external force actually having some impact on it, and there are just collisions with rain, so this momentum of motion should remain constant, doesn't change. But look, at the beginning it has some mass and some speed, and after, when I observe it, it has this mass. Mass is larger. So, but because it remains constant, it means that speed must get slower, because otherwise the momentum of motion will increase, but it cannot increase. It should remain constant actually here. So that's why logically the answer is, or the good answer is, the speed of this barrel will decrease because its mass is increasing, but the momentum of motion must remain same. And that's why its speed must decrease. In opposite way, actually, if we think about evaporation, again, I think you can apply it easier now. If I consider now the same barrel that continues going on, and now no rain is there, but the sun shines, and the water evaporates from it, its mass is getting less and less, and its water evaporates from it, we will notice that its speed is increasing. Right? Of course, we will never observe it in reality because of friction, but in a hypothetical case, decreasing its mass will increase its speed because of momentum conservation principle. And finally, let us finalize this last problem here. Well, the rest was sort of easy, I guess. So in order to find the speed of the block in the end, you just simply write that conservation of momentum applies, and you say mass of the bullet multiplied by speed of the bullet plus, I will use large letters now, mass of the block, speed of the block before the collision must be equal sum of them, m bullet plus m block multiplied by their speed after collision. So let's call it v prime. And from here, since the initial speed of the block was 0, so that was 0, you can simply say that the speed you are searching for is mass of the bullet, speed of the bullet divided by mass of the block plus mass of the bullet. And the answer will be very close to 1 meter per second. Yeah, so 1 meter per second is the answer. Please do not try to apply conservation of energy here, because conservation of energy does not apply, does not work here, because it is an inelastic collision. So the answer you will get is strange, is wrong. It will be some strange number. So always you are on the safe side if for collisions you apply conservation of momentum, not conservation of energy. And to find the friction, friction force, I think this is something that we learned a lot, what we can do well. You say it's kinetic energy was not conserved, was not remaining same because of the work done by friction force, which is mu mg s distance. And in the end, the body stopped, so it remains 0. So now you can simply apply this, m and m cancel, and the, oh, you're searching friction force. No, then you don't need to cancel m actually. Then you simply say friction force is mv squared divided by 2 times distance. Yeah. And then friction force should be equal 1 divided by 1.5 close to 0.67 Newton. So velocity is 1 meter per second, and the friction force is close to 0.666666 in a period. Oops, sorry. So just a moment. Okay, das heißt, das mit dem ersten Punkt haben wir alles gemacht, sind wir fertig und also Test Solutions haben wir alles besprochen. Ja, also war nicht so ganz einfach, aber wie gesagt, die meisten haben es sehr gut gemacht, sehr schön geschafft. Okay, jetzt for the pause, so before the coffee break, we want to spend 5 minutes of our time, or maybe 10 minutes of our time, for a small but very important principle of ballistic pendulum. It's gonna not take much time, but since it's so important, I want to make it with you before the break. And the ideas we discussed already today about what do you apply, how you apply, is energy conserved or not conserved, precisely these ideas will apply also for ballistic pendulum. But you simply can learn the steps, how you solve it. Let me explain what ballistic pendulum is. In the police or in forensics, you sometimes need to measure the speed of the bullet or to measure these high speed objects that are shoot from a gun, for example, or from a rifle. But now with high speed cameras, it is getting more easy, but still you need special equipment in order to measure precisely the speed of the bullet because it's too fast. You cannot measure it easily. But there is one method that is used in the police and in forensics, and this method is called ballistic pendulum method. The result you get is how fast was the bullet, how many meters per second was the speed. So typical speeds of bullets, they vary from, let's say, 50 meters per second to 300 meters per second, or even sometimes higher, and that's why it's quite a lot, of course. So the setup, this device, consists of a massive block hanging on a thread. Quite a heavy block having mass m large. I'll use this. Oh, let me draw it large M, capital M. And it is hanging at certain height, which we will take as 0 height. Now, some people who want to run this test, they take a gun and they shoot a bullet into this block, which is mostly made of plastic or wood. So I think you know what happens. You have a hanging mass, and as the bullet strikes it, hits it, obviously this mass will move, right? So it will move maybe like this. So it will move somewhere here because of the shot made. So now together with bullet is now in the block, it stacks in the block, and now together the bullet has lifted this block to some height h. And at this highest point, the block stops. So this height of the maximal elevation of the block you can measure. It's easy. And also you have mass of the bullet. It's also easy to measure. You have mass of the block. The only value that you do not know is the speed of the bullet. I will label it red, VB, and this is what we're gonna measure here. All other values we know. I will make them blue. Okay, die Frage ist, wie findet man die Geschwindigkeit von der Kugel, vom Bullet, wenn man die Werte m klein, m groß und h kennt? And here, please, you have to be very careful because I know that many students do a mistake here. What you cannot apply here directly is the conservation of energy. The conservation of energy is not applicable here because it is an inelastic collision. Because these two bodies stuck to each other, it remains in the block, it is an inelastic collision. So energy conservation does not apply for the bullet hitting the block. But we have a good news. As always, as for any collision, conservation of momentum can be applied. That means the first step in solving this problem, in finding the speed of the bullet, is to write the equation for conservation of momentum. And we remember that conservation of momentum applies for any direction, right? It is a vector and it applies for any direction. Which direction should we take? Well, since the bullet goes in horizontal direction, we should take horizontal direction as our direction. So we will apply conservation of momentum in this direction. So let's do it. V bullet, M bullet plus M block, V block. It has zero speed actually, so this is 0, is equal the block and bullet together move now with some speed v. So this speed in this direction. Let's call it v prime here also, v prime. This is this speed, v prime. In other words, speed of the bullet which we want to find is equal m large plus m bullet multiplied by v prime divided by mass of the bullet. Do you see a problem we have still here? What's the problem? Why it is not solved yet? Why it is not answered yet? Just half of the answer. Okay, so maybe more responses. So so no height at the moment, yeah. So height is not included, but maybe I found a way to solve it without height. So what's the problem? Why I cannot find this speed of the bullet now? What prevents me from finding the bullet speed by using this formula? Okay, the problem is obviously that I do not know what is the speed of the block and the bullet. Yes, this v prime we don't know. So we again, it's very at the first moment when the bullet hits the block, it gives the whole block some speed, but we haven't measured this speed. We don't know how much it is. We only can see that the block goes to some height, but we have no idea about how fast was the block at the moment when it was hit by the bullet. So this v prime, I label it black to show that we don't know it. So that's why what we got is just a half a solution, part of solution, first step of the solution. Now we have to solve it, and this time we need to find V prime. And you remember that at the beginning I told you that the conservation of energy does not apply here because the collision of the bullet with the block is inelastic, and for any inelastic collision, only momentum is conserved and energy is not conserved. But now it is over. The collision took place. It's over now, so the bullet is in the block now, and the collision is finished, and we applied the conservation of momentum to analyze the hitting, the collision. So now it is over, so they now move together, and at that moment we have like a pendulum, normal pendulum, where friction forces are negligible, or we can forget about friction forces. And from that moment on, we can apply conservation of energy. So now the bullet is sitting in a block, and from this moment on, conservation of energy applies. It is true now. So that means after collision took place, now my block and bullet together, they got some kinetic energy, which is equal m large plus m bullet v squared prime, so this is their speed together, divided by 2. So this is the kinetic energy they gained together at the very beginning after the hit. And without losses, they reach certain height h, which is associated with some potential energy equal to m plus mb g h. From here, we can cancel these two masses. And from here, we can say that V prime is equal 2 times GH square root. So we found this missing V prime by using conservation of energy, but only now, only after collision, not before. Now we can apply it. And so now we are ready to solve this problem, and now it is solved. We simply write the final solution. Speed of the bullet will be equal mass of the block, of the wooden block, plus mass of this bullet multiplied by square root of 2 times GH divided, all divided by mass of the bullet. I'm just waiting for my tablet to unfreeze. Yeah, okay, now it worked. So this is the final formula, and indeed you see we used the mass of the wooden block or plastic block here. We used our knowledge about mass of the bullet here. And we needed to measure the height indeed. But the main trick here was that we couldn't use it directly. Just many people say, oh, okay, bullet hitting the block, no problem, I apply conservation of energy, one formula, tack, tack, ready. I'm ready, great. And it is wrong. So you must be careful here. You should divide this problem in two parts. At first part, you apply conservation of momentum, and on the next part, you can apply conservation of energy. And this is the answer that you should get. If you like, of course, you are allowed to solve this problem backwards. So that means you first analyze the motion of the pendulum and apply conservation of energy, and then chronologically backwards, you analyze what happens when bullet hits the block, and you apply conservation of momentum here. So, of course, you can make it vice versa. First, formula number 2, and then formula number 1. Doesn't matter. In the end, you will get the same formula as your final answer. So, that was one of the most central points in the topic momentum and energy conservation, and also must know for all of you, because this is something that you should be able to do anytime, easily, and if this problem appears in your final exam, you should say, yes, I can solve it quickly and easily, and I will get 15 points for this problem, which is a good thing. So now let's start our coffee break, 15 minutes long, and after the coffee break, we will talk about elastic collisions specifically, absolutely elastic collisions. That will be our next topic after the break. So see you in 15 minutes. Okay, hi, wir machen weiter. Ja, kam gerade die Frage von Emmanuel. Wenn ich das richtig verstehe, so if I got you right, basically such an analysis is possible. You just have to be careful that for any impact, you can apply conservation of momentum at any time. So during the impact and after the impact, but concerning the conservation of energy, you must be just careful. Strictly speaking, at the moment the impact takes place, you cannot apply conservation of energy. And mostly we just need to check what exactly we can measure, what kind of information we can get from our objects. Because in many cases, measuring forces directly is not possible. I want to give maybe one little example now before we start with absolutely elastic collision, just to give an idea what's the range of forces that might be involved in such collisions. Let me just, together with you, let us solve one very simple and easy example where we will calculate a force in a collision. Oh, let me just take some resting ball here even. So as we found out, the Newton's law says that if we want to find something about force, so force will be basically found as how quickly the momentum of motion changed. So it will be dP over dt. And that means in any problems where we are asked about forces, we need to know the duration of the impact. So let's just check how it works. Let's consider some snooker game, you know, these billiards or snooker games where you let plastic balls to hit each other. And let me have one plastic ball and another plastic ball to have a contact. And so typically, I don't think we need to measure it precisely. Okay, let's measure it still. What do you think? What's the mass of a snooker ball? I have no idea at the moment. Maybe like 100 grams, maybe. So let it be 0.1 kilo, just to make it close to reality and easy to calculate. And let it move with the speed of 10 meters per second to make it also quite a quick ball. And it hits some other ball which is at rest. So now if I measure the time contact with high-speed camera, I can find out, I check this number, that the duration time of impact is quite short. It is 0.0002 seconds. Really short. This is the time where these two elastic balls really hit each other. So this will be an absolutely elastic collision of very hard snooker balls. So, and now I'm just wondering, how big is the force in Newton with which these two balls are acted on each other? Let's do it. I guess there will be quite a big number. Let's measure. So first of all, I'm using the same formula. So basically, at the hit each other, the momentum of one of the balls will change from mv to 0. So as you hit each other, they will probably, one of them will stop and another one will start moving. So I think the force I can get as change of momentum, which is from 10 meter per second multiplied by 0.1 kilogram minus 0. Minus 0 because in the end it will stop. So final state. Divided by the time of the impact, duration of the impact, which is 0.0002 seconds. So let us check. I will open my calculator here also. So 1 divided by 0.0002. Well, and the result I got is 5,000 Newton. Which is quite a big force if you think about this. And indeed, what we see, forces actually acting upon collisions are pretty great forces, pretty big forces. If the time of contact is really short, then the forces are really appreciable. So from the force, it is like you have 500 kilo body, the weight of 500 kilogram body. That's a lot. But we are just simply speaking about two snooker balls, two plastic balls hitting each other. So amazing how big are the forces that are involved in such collisions. Of course, the forces are acting only for a very short period of time, right? But those forces are responsible for big acceleration of the bodies, right? So no wonder that such forces, well, may appear. So big forces could be. Actually, our main goal now is to talk about absolutely elastic collisions. In general, we separate collisions into three classes. So to the first class, to the first group, belong collisions that are absolutely elastical. Absolutely elastic. And in that case, we can both say that momentum is conserved and energy is conserved as well. So they're both conserved. Then the second group will be partially elastic. So this is most of real cases we deal with, like tennis ball, jumping, or table tennis ball, or many other collisions. They are not absolutely, but sort of almost elastic. In this case, the energy conservation does not apply anymore. It is not applicable. We only can apply conservation of momentum. And the level of elasticity we can judge basing on so-called restitution coefficient. I'm not giving too much about the restitution coefficient because it is never asked in our exams. So I just don't want you to learn many things that never appear in your later study. But just for your information, there is such a number which is called a restitution coefficient. And it characterizes how elastic the collision is. So if the restitution coefficient, let's call it K, if it's equal to 1, then it is absolutely elastic. If it is equal to 0, then the collision is absolutely inelastic, so they stick to each other. But for a partially elastic collision, the restitution coefficient can be, for example, 0.5, right? Or 0.3, or 0.185, whatever. So it just tells you to what extent the energy remains conserved. So 0.5 means it's sort of half elastic, so approximately half of the energy gets lost. So roughly. Okay, and the final group, we said, so they are absolutely elastic, absolutely partially elastic, and then the last group is absolutely inelastic collisions. Well, obviously, this is the case when the two objects stick to each other, stick together, and in this case, the energy losses as heat are maximal, and in this case also we say that only momentum is conserved. You see, in all collisions, the momentum of motion is always conserved, you can always apply it, but energy conservation can only be applied for description of collisions that are elastic. In that case, you can apply energy conservation before collision and after the collision, so it remains conserved. For ballistic pendulum, the problem we analyzed before the break, we could apply conservation of energy, but only after collision took place, not before and after. So because before and after, it haven't remained same. Only after it happened, we could apply the concept of conservation of energy. But if the collision is elastic, then you can apply the conservation of energy anytime. Now let me show something to you, maybe just for fun, and this will be, have you ever thought why the police, they use rubber, sticks, rubber weapons? So why it is made of rubber? So there is an interesting physical explanation why the police forces, they use how's it called rubber, no, it's called not rubber sticks, but I've forgotten the name. Just let me see how it will be in English. Clubs, yeah, it's good, yeah, thank you. So sort of rubber clubs, and also they use rubber bullets, yeah, so such thick things that hit you. So the reason for that is they don't want to actually to damage, yeah, your body, but they want it still to be painful, just to make it more painful, because if they use some not elastic objects, it will be less painful for contact. Let me now show how physically a rubber object which will produce more pain than not elastic object. So let me show how it works. So look, if we have some object and some rubber ball, will hit this object. So its speed will be v and mass will be m. And now, as we know, if it is an elastic collision, absolutely elastic, then it will rebound having the same speed as before, but in the opposite direction, right? So after it hits you, it will rebound back having same mass and speed, but in the opposite direction. So the change of the momentum just a moment. I'm still waiting for my software to react. Okay, so the momentum change, now, will be actually m multiplied by v minus m multiplied by v, because because it is now in the opposite direction. So actually the change of momentum will be twice m multiplied by v, 2 times m multiplied by v. Okay, you got it, right? So it is twice mv, because once it was mv in one direction and now it is mv in the opposite direction. So the difference change is actually minus, so which gives that twice mv. And the corresponding force which is applied on the body in this case is 2 times mv divided by delta t. And if I take some not rubber object but some more sticky cloth, so some sticky object, then in this case I will draw it again. It again hits my body and remains stick to it, which means its final speed is 0. Energy is lost. So a change in the momentum is simply from mv to 0, which corresponds to just mv. And the force that is exerted on my body is simply mv divided by delta t. So now look, we have really clear difference. If you use some elastic rubber-like object that hits your body, the force you produce here is 2 times mv divided by delta t. So it makes a bit more pain as compared to a sticky object that sticks to your body, and in this case it is just mv divided by delta t. So maybe in the future, if you have a choice to which object should hit you, then always choose less elastic one, because it will produce less pain physically. So, yeah, sure, I can repeat it a bit, no problem. So, in other words, for real collisions, it really makes a difference if the collision is elastic or inelastic. So let me draw it one more time for an elastic, absolutely elastic collision. Elastic means that no energy is lost, and you have, before collision, your speed goes like this. Just a moment. This is your speed, v. And after collision, you have speed in opposite direction. And this is the speed is a vector. So if we use this projection to the right, then this speed will be minus now. Why it is not drawing? So if this our direction, this is minus speed, and the change of the momentum delta p is equal mv minus mv. So mv minus mv, which is equal 2 times mv. So obviously, the change in the momentum is bigger here, as compared to the case when the object just reaches your body and sticks to it, because it is so adhesive, maybe. And now it just sticks, so now its speed here is equal to 0. Then change in the momentum is equal just mv minus 0, which is, mv, which is simply mv. So just what I wanted to say to you is, using elastic collisions, or basically elastic collisions, they produce more force on the surface. They produce more force as compared to sticky collisions. And that's why for all-day situations, for some situations, contacts with elastic objects are more painful or can hurt you more as compared to inelastic objects. They just stick to your surface. So just think about maybe two balls. You may make a snowball which will hit your body and will remain stick on your body, or you may have a rubber ball of the same mass. It will hit your body and bounce back. And so this hit by rubber ball will be more painful for you as compared to a snowball. Snowball will produce less pain. But this is actually just sort of additional information for you, just to see how physics apply for real world. Now I still want us to make some important for the exam, and this last important point will be specifically about elastic, absolutely elastic collisions. I want us to study these elastic collisions more carefully, because they are sort of very influential, very popular in physics problems. And maybe even if you are a strong student, you might now discover some new aspect, something that you haven't known before. So this is at the beginning. Let them have mass m1 and m2, and this speed will be v1, and this speed will be v2. And it will be a central collision, because if they collide not centrally, they will have some angle, and it's a lot of headache we don't want to make this cosine, sine things. We just make it simple. They collide centrally, and what happens? And so this is the first case before the impact, and 2 will be after the impact. So we have again M1, M2, V1 prime. I will use prime to show after. V2 prime. Okay? So now let's take a look what we know about such an absolutely elastic collision. And here we have a very special case, because for an absolutely elastic collision, both the momentum of motion and the energy will be conserved. So let me write it here down. So what is true for such collision is M1 V1, I will use vector relation now, plus M2 V2, again as vectors, equals M1 V1 prime plus M2 V2 prime. Since I'm using the vectors values, I'm not talking about some specific plus and minus. I'm just saying vectors in general. I'm not talking which one is plus, which one is minus. I'm just regarding them as vectors, as vector values. And as it is an absolutely elastic collision, I can also say that, just a moment, yeah. M1 V1 squared plus M2 V2 squared divided by 2 is equal to M1 V1 prime squared plus M2 V2 prime squared divided by 2. Well, since I have 2 and 2 in both parts, I can actually simply get rid of them. 2, I can get rid. And this is the conservation of energy. Again, let me emphasize here to stress out is the first equation, conservation of momentum, and the second equation, conservation of energy, they look quite similar. And many people would say, isn't it obvious that if 1 is true, then 2 should be also true? But the answer is no, not. These are 2 totally different equations. And the fact that some sums of numbers are equal to each other does not imply that the squares of these numbers also are equal to each other. Mathematically, these are 2 different things, not related to each other. So just think about some simple numbers. If you have, let's say, 2 squared and 3 squared equal to 1 squared plus 4 squared, so not squared. They are equal, not squared, but if you make squared, they will not equal to each other anymore. So these are not same, this is not same equation. These are two totally different things. But still, a good news for us is that we can combine them now, and by combining these two equations, we can derive one last equation, which will ultimately allow us to find the speed of the first mass after collision and the second mass after collision. So the goal is to find how do we find V1 after collision and V2 after collision. And we can find them from these two equations. So let me draw the formulas for you so that you can see them. And it would be perfect if you write it down with me. So V1 after collision can be found as m1 minus m2 v1 plus twice m2 v2 divided by m1 plus m2. And v2 prime is equal, this time it is m2 minus m1 multiplied by v2 plus twice m1 v1 divided by m1 plus m2. So please write this equation, make a note. Please write these two equations because they're gonna be useful for you. As for your question, can we be asked to find the impulse of body A on V during impact? F multiplied by T. But the formula you write here, F is equal M multiplied by V minus U. It is not the force. It will be just change in the momentum, and the force will be changed in the momentum divided by time. Well, it may occur, and if closer to the exam, if I know more what kind of questions we should expect, we will specifically exercise for that. But usually in the final exam, we only have some problems related to collisions. And some of them you already solved today in the test number 13. So these were examples of our previous midterm and final exam questions. And also the questions I am giving today to you as homework, as your test number 14, also you will see what kind of questions you mostly have in the final exam. So I'm always using the exam questions for our exercise. Yeah, that's why it is so important and useful that you do all your homeworks. It makes you better prepared for your exam. So I would say specifically if you ask about impulse and force, mostly they don't ask it. But still it would be good if we train ourselves, right? So that's why I want to do some more exercises with you. We'll find force and time and impact just to have better feeling about it. Okay, thank you too for the question. And I hope meanwhile everybody have managed to write these two equations that you noticed them. Well, of course, a good question is always, do I have to write it by heart? Do I have to learn it by heart? The answer is actually not. You don't need to learn it, but it is an advantage for you if you can learn it or if you can derive it by yourself. Since, if we would study medicine or chemistry, I would say, come on guys, you don't need it. But since we are talking about engineering profession and engineering specialization, as an engineer, of course, you must be able to have better knowledge in physics, which means that either you remember these equations or you can derive them as you wish. So, as for me, I don't remember them, but every time I need them, I just create them new, and it's your decision. So you either just have them in front of you and memorize them, or you just simply say, okay, it's easy. I just simply need to combine the conservation of energy and conservation of momentum, and I can find these values from here mathematically. Both is okay, it's up to you, but this equation might be useful for you in your problem solving. Okay, so that's why we are spending so much time with these two equations, with these two formulas. And in order to show their power and their beauty, I want us together to check different scenarios and to see what happens if we apply these formulas for different cases. And in some cases, we will see logical things, and in some cases, maybe we will see some not logical things, some strange things happen. Let us check it. So, first case I would like to consider with you will be the bodies have equal mass and the initial speed of the second body is equal to 0. So let's predict what happens here. Just look at the formula and please see that in this case, this term 2 times m2 v2 gets to 0. As well as the previous term, m1 minus m2, it gets to 0, right? So it simplifies dramatically. So what do we have actually as result of our calculation is that the speed of the first body after the impact will be 0. Will now become 0, and the speed of the second body after the impact will be precisely equal to the initial speed of the first body. In other words, these two formulas predict the following behavior, which is logical. You have two balls of equal mass, one is at rest, another is approaching it. After collision, they exchange their speeds. So now the first ball, which moved, now it stops, and the other ball, which was hit, now starts moving with the same speed as the first ball. So they exchange their speeds. This would happen also in the case if initial speed of the second body is not zero. So let me show it. We have again same masses. M1 is equal to M2. And this time V2 will be not zero. In this case, the calculation shows that after collision, after these two bodies collided, the speed of the first body after collision is equal to the initial speed of the second body, and the speed of the second body after collision is equal to the initial speed of the first body. So in both these cases, 1 and 2, if you have bodies of same masses, and if they collide, what always happens, they exchange their speeds. So the first body gives its speed to the second body, and the second body gives its speed to the first body. Even more, they exchange velocities. Not only values, but also directions are shared. So let me write this rule, what we established, by using these two formulas. If two bodies of equal mass collide, they always exchange their velocities. I will now make some space for us, because I want to analyze together with you a couple of more scenarios just to see the power of these equations. Sorry, it just takes time. Okay. Okay. So now let's consider the next case. We're still doing everything around these two formulas, just to checking how good they are and how useful they are. Let's now consider the next case, which will be bodies, they have different mass. M1 is bigger than M2. And the second body is initially at rest. So can you predict what happens? Just imagine there are two balls. One is at rest, and a heavier body is approaching it. So what happens? This is smaller one, bigger one is hitting it. So what do you expect? So obviously the smaller body, which was hit, will now move in same direction, right, as bigger body. But as for bigger body, we probably also assume that it will continue moving with in the same direction, but just slowlier than before. So let's see what mathematics tells here. It says that the speed of the first body after collision will get less as compared to initial speed. And the speed of the second body after collision will be now, of course, bigger. And logically, the more massive the first body was, the bigger will be the final speed of the second body, which got hit. Just a moment, yeah. So, yeah, please go ahead.
I wanted to ask, oh my God, I just forgot my question. I wanted to ask, is it possible to have an elastic collision where two bodies come from, like, towards each other, then they end up moving in only one direction, but it's elastic still?
Oh, good question. Yeah, good question. This is actually exactly what we're going to study. Thank you for the question. This is a good question. So I just imagined there are two objects, so they collide to each other. One big, one small. They collide absolutely elastically. And the idea is it actually possible at all that after collision, so they both go same direction? So is it actually possible at all or not? This is what we are going to analyze now. Very good. So this is what we're going to do. And so let's consider the next case where we have now the second body more massive than the first one. Now it will be M2 more heavier than M1. And initial speed of my second body will be again 0. I think now you can also intuitively predict what happens. Just think about two balls now. The heavy one is at rest, and the lighter one hits it. So what would happen? I think the heavier will start moving now in the direction of the hit, but slowly, and the lighter one will rebound in opposite direction. So it probably will change the sign of its speed. Let's check what happens, what the equation tells us. It tells us that now the speed of the first body after collision will be equal minus, which makes sense, so it rebounds, so it is now minus m2 minus m1 divided by m2 plus m1, everything multiplied by v2. So what we see here with this minus, it shows that indeed now it moves in a backwards direction. And what about v2? We expect it to move forward plus, but slowly. Let's see. But slowly. So it will gain some speed a little bit. So let's see. It will be 2 times m1 divided by m1 plus m2. Well, yes, it makes sense. So again, it will be similar as the previous case. So they are sort of similar, but we see that it will continue moving in the initial direction. So in other words, after they collide, the small body will move here, and this large body will move here. This is what these equations predicted. Good. So, and now I think coming back to your question, so let me first ask it for the whole group. What do you think now? So, can it ever happen that we have 2 balls of different mass, that they collide, and after absolutely elastic collision, they continue moving in the same direction? Can it ever happen or not? So what do you think? Yes, the answer is yes, I agree with Omar here. In this case, it may come true if we have really different masses of the body. So, in other words, let's consider a very heavy object is moving against a very light object. So, at the moment that they collide, this heavy object is so inertial, it continues moving, and the light object actually cannot oppose the heavy object. It will still move in the same direction. So now, if the mass difference is big between them, then they both will move in the initial direction of this heavier object. And this brings us to an interesting practical case. And this is, for example, about a train. I think many of you already experienced, so when you are in the train and you know that how dangerous can it be, then if you're driving a train or you're sitting in the train and something is on the railways. For example, a car is on the railways. It can be very dangerous for both train and the car, because the people in the car can be, hurted, but also people in the train are also in danger because they also may experience some injuries and the train may go off the road. And from the equations we just discussed, some interesting consequence appears, which is not very intuitive. Imagine you are sitting in this train and you are the driver of this train, and you're seeing in front of you there is a car, light car, standing on your way. And there is no time to brake. You know that you will hit this car. You cannot avoid it anymore. Or there is a person there or a car. So the thing is that if you try to decrease your speed, you still will hit this object and you will still hurt these people, but also your train will be in danger because your speed is not high enough, and actually both of you will be damaged or hurted by this impact. What physics tells us in this case, since you are driving the train, which is much more massive as compared to this little car, your goal physically will be to increase your speed even, so that after you hit this car, well, the car will be basically eliminated, of course, but people in the train and also the whole your train will continue moving in the same direction with approximately same speed without being affected by collision. So you will save all people in the train if you increase your speed in this case. Sounds strange, but this is what these equations predict, right? If you are driving a very heavy, massive object, you can minimize the damage of a collision if you increase your speed. So in that case, you will make both objects to move in the same direction. Yeah. Of course, my example with the car and the train is a non-elastic collision because they will probably, the car will remain stick to the train, but still it shows just how not intuitive things are sometimes. I'm just checking if we have to take some more cases. But I don't want to make it too much. Maybe if you like to play with these different scenarios, maths is different, speeds are different, you can go ahead, but I don't think it would be important for all of us because otherwise it gets too much complicated. So let us take it as a take-home message that for an absolutely elastic collisions, there are these two useful formulas that predict a lot of things about how actual central collisions will take place. So the power of the formulas is that you can imagine different scenarios, bodies having same mass, different mass, same speed, different speed, and in all cases you will have some valuable predictions about how the situation is going to develop in the time. Well, if you like it, indeed, I can just offer to you, consider two more cases, maybe, if you like, if mass of the bigger body, M1, is much, much bigger than mass of the smaller body. So let's consider, please take it as an additional bonus homework. Please check what happens to this equation if the M2 is negligible small as compared to M1. Then again, you will see some interesting thing happening. So consider the case where M2 is almost 0 as compared to M1. You can do it, and I think it will be better if you do it by yourself, because you can learn more if you play with those things. Like, I think it makes a lot of fun if you do it by yourself, actually. I promise that we will talk about collisions next time again in seeing how the formulas work. But now, to finalize today's class, as I promised, one last chapter that remained to us. I promised to talk about the rocket motion. And just let me, in the remaining, let's say, 20 minutes of time, I would like to tell you something which is not directly related to the exam, but since can be interesting and funny for you if you are interested in how physics describes the world. And I just want to show how conservation of momentum is involved into rocket motion. So first I will save this. So if you're already tired, you can actually relax now a bit, but I still do hope that you have energy for 15 or 20 minutes concentration, because I'm going to introduce the concept of thrust, and we'll see how thrust appears as a result of, or as a consequence of, conservation of momentum. For that, let us consider a rocket which is at the moment already hanging somewhere in space, so far away from the Earth. It has some fuel, but at the moment it's not moving at all. So that means we can consider this rocket as an isolated system separated from the rest of the world. So this will be fuel of the rocket. I will make it red. So at the beginning, the rocket has 0 speed. In order to make the rocket motion mathematically addressable, we need here to separate two things from each other. The first thing will be the fuel of the rocket, the combustion process, so the exhaust that will be created. And the second thing will be the mass of the rocket as inert body. So in other words, we will need to consider fuel and the rocket body as two different objects. So I will call this rocket body, I will call it M rocket, and mass of the burning fuel, I will call M fuel. Don't worry, it's not going to be much mathematics. There are simple couple of equations. And look what I have at the beginning. Since fuel and rocket are same thing and they don't move, we can write the conservation of momentum here as m rocket plus mass of the fuel. It doesn't burn actually. So together multiplied by V0, which is 0, right? So this is what we have at the beginning. So everything is equal to 0. And now we want the system to move. Now we want the rocket to move. So the motion of the rocket will occur if we start the combustion process. So if we launch the chemical reaction, that the fuel will be, we have an exhaust of fuel, it will be pushed backwards, and by doing so, it will push the rocket forward, exactly as we did today in the homework about the air balloon, right? So same principle, but this exhaust, we will now look more carefully. So now we will say that initially we have 0, and after we ignited the fuel, we will have mass of the fuel, burning fuel, multiplied by speed of the burning fuel plus mass of the remaining rocket multiplied by the speed that rocket gained, right? So now I will write it one more time. I will draw it again. So this is our rocket. Now it is, the fuel is burning. So the rocket is flying with speed Vr. And the fuel is pushed backwards or downwards with speed Vf. So now, if I write it again, I can write it like this: m fuel multiplied by v fuel equals m rocket multiplied by v rocket. Well, with minus sign actually, right? Minus, because they are in opposite direction. Now I'm moving from vectors to projections. So now I want to use just numbers. I hope this is clear so far, and we can do one more step to reach the beautiful central equation of the rocket technique. This is not yet. We simply have written the conservation of momentum principle, but I want us to do one last step. And in order to do it, I want to ask a question now. What should we do now with our equation in order to convert these values into force values? Think about this, please. You know the answer, but I want you to think about this. Now we have a conservation of momentum equation. What should I do with both parts of this equation in order to have force on the left and on the right side? What shall I do? What kind of mathematical, physical thing I must do here in order to convert momentum into force? You can either write it to me over your chat window, or you can switch, I can switch your mic on. Yeah, thank you for this answer. Yes, I agree, but it could be formulated a bit more precisely. What shall I do here? I agree with what Mom has written. It's good that we need to consider time here, but can somebody please write precisely what do we need, how do we need to put time here into this equation? What shall we do? Remember how second law of Newton is formulated? Force is, so this will help us to find the answer. Okay, so in this case, we simply need to divide it by time. It's obvious for two reasons. So we need to divide both parts by time. You know why? For two reasons. One reason is, first, in order to get force, force is change in the momentum over time, right? So over time, per time. This is first reason. Second reason is we know force is m multiplied by acceleration. But what we have in the equation now is mass multiplied by speed. In order to convert it into mass multiplied by acceleration, we need to divide it by time one more time. Mass multiplied by speed divided by time, right? Because speed divided by time is acceleration. You see? So in other words, let me now make force aspect here visible, and for that I will divide both parts by time. Let's take some period of time delta t. I divide both of them by delta t. So look what happens. Nothing special, right? But it will change now. If you look carefully, a little bit carefully, what's going on here? What actually changes with time as the fuel burns? Just imagine the fuel is burned, is exhausted. And with time, we have less and less fuel, right? So mass of the fuel will change with time. But the speed of the burning, this Vf, it remains constant. You agree? So actually this like exhaust speed. So once you ignited it, it's burning. But the fuel is getting less and less. So that's why I can write it like this. Delta M fuel divided by delta T multiplied by speed of the burning of my fuel. It's sort of constant. And now think about the rocket. The rocket is so big that we can say its mass remains constant. But what happens is, because of the fuel burning, the mass of the rocket the speed of the rocket changes with time. So let me rewrite this equation this way. So the things that remain constant, or almost constant, I will make red now. We're almost done. The very last thing that we require here is just to see clearly what we got here in the right part. What is actually V delta V divided by delta T? It is an acceleration, right? So what we got on the right part is mass multiplied by acceleration. So what we got is the force that drives the rocket, that makes it accelerating. And this force, what we discovered, that accelerates rocket, is called thrust. Let's call it FH. And now I will write it one more time to make it last final thing. Thrust of the rocket is equal V fuel multiplied by dm fuel divided by dt. Now instead of delta t, I will take shorter time, dt. So look, as any engineer, you want your rocket to fly as good as possible. It means that for most of space missions, you want your rocket to gain speed as fast as possible. You want the thrust to be maximal, because if the thrust of your rocket is not good, then you are a bad engineer. So, and this equation is the central equation of a rocket science, because it tells you two things that you need to have in order to make your rocket to be good. And let's take a look, and then we will finish this class. Let's discover the beauty of this equation. It tells you in mathematical language, in order to build a good rocket, you have only two tools in your hands, only two options. Either you make your fuel to burn very well. You need to increase the exhaust of your fuel. You need to increase the speed of this burning fuel, or this orange thing here in the rocket. In other words, you need to make this burning process very quick, like an explosion actually. And in this case, your rocket will fly really good. But you know, this is a dangerous thing, because the closer you are to the explosional chemistry, the more unstable it's getting, right? So here we have some limitations, and in most of rockets, I know that this speed of exhaust cannot be actually more than 100 meters per second, so it's dangerous if it's higher. So the first option you have in order to build a good rocket is to increase the speed of the chemical reaction, making like explosion. And the second tool, and only one, you don't have any other, is to do what? Can somebody maybe describe it with your own words? What does this dm over dt mean? How do you understand it? What does it mean? dm fuel over dt. Can somebody write how you feel this value? You already studied probably differentiation in mathematics, and in physics we talked about differentiation. So what is dm over dt? dr over dt is for the rocket, it is, oh, what do you mean with dr? The mass of the rocket remains sort of constant, right? But speed of the rocket increases. But for the fuel, it is vice versa. We say that the speed of the burning of the fuel remains constant because this is the speed of the chemical reaction, but the mass of the fuel is decreasing. And look, what this dm over dt tells us, it is the rate of fuel consumption, right? It is showing us how quickly the fuel is consumed. In other words, the second tool to make a good rocket, to make a powerful rocket, is to build such an engine that it will burn lots of tons of fuel per second, so that the fuel consumption will be large. And that's why, unfortunately, most of modern airplanes and rockets, they consume lots of fuel per second. So if you're flying with an airplane, you probably know that such an airplane per second consumes approximately 1 ton or 2 tons of fuel per second, per 1 second, which is, well, no, sorry, I think it was a bit less than 1 ton, but still a huge number actually, a lot of liters of fuel per second. But actually, these are just 2 options that we have, and this is what physics tells us. That means, strictly speaking, that's why we cannot actually build any rocket, whatever we like, to make it as fast as we wish. There are physical limitations, and those physical limitations that are in a modern rocket technique is that you cannot chemical reaction to occur faster because it's already very quick. And the only thing you can actually do is to make your engine more and more hungry for fuel, right? So it needs to be able to burn a lot of fuel per second. And this is basically true. So most of rocket engines are really gigantic, right? So they are really huge. Okay, that was just a final note in today's class, where I showed to you that how simple considerations related to conservation of momentum bring us to fundamental conclusions about building rocket technique. And this equation which we saw is the fundament of modern rocket technique, right? So actually those two things, so the equation governs the modern rocket technique. Fine. Then let us finish now. Let me remind you that I'm going to send the drawings to today's class notes as well as the video, and also our next test to all of you by using both our EduPage system and Ilias system. And as always, I will be glad to get your feedback, your solutions for your next test. I hope that the next test will make a lot of fun for you, but it's gonna be a bit challenging. So please take a look. It could be an interesting challenge for you, the next test. But please still try to do as much as you can. So with that, I wish you a nice week. Stay healthy, and we see us next time. See you. Goodbye.